Hello my friends, and welcome to this new practical activity of part 9 dimensionality reduction. So in the previous section we experimented with PCA, Principal Component Analysis, and we indeed got great results with our wine dataset, which will be the same dataset for this new section because we want to compare several dimensionality reduction techniques. So there we go, we're going to see if we can even beat PCA, which only had one incorrect prediction. So we're going to work with the same data set, and therefore the implementation will be exactly the same except one cell, which will be the cell, of course, where we implement LDA instead of PCA. All right, are you ready? Let's do this. Before we get into this folder part 9, let's make sure everyone here is on the same page. I gave you the link to this folder containing all the codes and datasets right before this tutorial, so make sure to connect to it. And now here we go. Let's enter part 9, dimensionality reduction. And now we're going to go into section 44, Linear Discriminant Analysis, LDA, which will be a new technique of dimensionality reduction, very powerful as we will see. So let's start with Python as usual, and there we go. This folder, just as the previous one, has two files. This is the implementation, and this is the same wine dataset, which belongs to a wine shop business owner who first asked you, the most talented data scientist, to do some clustering to identify different customer segments for each of the wines of this data set. Each row of this data set corresponds to a certain wine, and for each wine we have several wine features or characteristics, all these up to here, and you used all these features to identify those three customer segments or customer clusters. And after which, since this wine shop owner was so happy and impressed by your job, well then of course the owner asked you to do another mission, which is the one we're about to do with LDA, which consists of building a predictive model combined to dimensionality reduction applied to this dataset, so that for each new wine that this owner has in its wine shop, well, by deploying this new predictive model, this owner will be able to predict which customer segment this new wine belongs to, so that it can recommend this new wine to the right customers and therefore optimize eventually the sales. All right, so that's exactly the same data set. And now let's move on to our implementation, Linear Discriminant Analysis, which we can either open with Google Collaboratory as I'm doing it now, or Jupyter Notebook. And as you notice, I kept this previous implementation we did on PCA so that we can compare the results in the end, right? This is PCA, this is LDA, but since this is in read-only mode, we're going to create now a copy so that we can re-implement that cell that builds the LDA model. So there we go, save a copy in Drive. This will create a copy inside which we'll be able to re-implement the LDA model. All right, and now we can, close this so that we can have the two implementations next to each other, the two copies. And now let's do this. Let's quickly remove, the cell that implements the LDA, this one, and let's re-implement this because, all the rest is the same. I will actually remove all these outputs here so that you don't see the final results and we can keep them as a surprise. So let me just remove the outputs too. Don't look too close, and there we go. All right, so basically all the cells of this implementation are exactly the same as the previous one, PCA, except of course the cell that implements LDA right here. So no need to re-explain all this, plus all these other cells result from our diverse toolkits, so you're definitely 100% familiar with them. All right, so let's do this. Let's, apply LDA. So we're going to create a new code cell, and there we go. Let's implement Linear Discriminant Analysis. So now you have two options. The first and the best option is to press pause on the video and try to implement this yourself by, of course, browsing the Scikit-learn API and find that LDA class that can implement that LDA dimensionality reduction technique, and you will definitely end up with the same solution I will implement in a few seconds. And the second option is, of course, to, well, not press pause on the video and implement with me the solution in, let's say, 3 seconds. 3, 2, 1, and go. All right, let's do this. Let's implement together LDA. So, as I've just said, we're going to implement LDA thanks to the Scikit-learn library. Therefore, we're going to start from Scikit-learn, from which we're going to get access to, this time, not, let me go to PCA here, not the decomposition module of Scikit-learn, but a new one, which is very easy to remember because this is actually discriminant underscore analysis. Okay, that's another module of Scikit-learn that contains, of course, the class that can implement LDA. And that class, well, after this import here, we have to add the name of this class. And the name of this class is capital L, and then very simply, Linear Discriminant Analysis. All right, very good. The reason why Google Colab, by the way, is not helping me with the suggestions is because the notebook is not running. And remember, to run the notebook or, to connect it, well, you need to either run any of the first cells or upload the dataset. So let's do it right now so that, Google Colab can assist me. I really love it when it does it. So right now I just clicked on this folder button, and then let's click the upload button. And we will end up in the previous folder for principal component analysis. But let me show you the path again. I put my machine learning A to Z folder in my desktop. So inside we're going to go now to part 9 and then section 44 linear discriminant analysis, then Python, and then wine. All right. So this is exactly the same data set as before, but I just wanted to show you the path. All right. And there we go. We have the wine. And so now I'm going to show you, if I retype this, linear discriminant, see, now it is helping me. So that's maybe better to have, this reflex to upload the data set right at the beginning. Okay, so linear discriminant analysis, but since this class name is actually pretty long and pretty not practical, well, let's just, add a simple shortcut like LDA. We can do this, that's totally fine. And now let's press enter to move on to the next step, which is, of course, naturally to create an object of this linear discriminant analysis class. All right, so of course we're going to call it LDA, right? And now we're going to call this class, and since we gave it the shortcut LDA, well, we can simply call LDA this way. And now, well, exactly the same as before, this LDA class needs to take as input only one argument, which is exactly the same as before, and also it has the exact same name. It is n components, which corresponds, of course, to the final number of extracted features you want to end up with after applying this dimensionality reduction technique. And of course, as I recommended in the previous section, we're going to start with 2, so that we can see if, even with only 2 extracted features, well, we can get great results. And if that's the case, well, not only we'll get great results, but also, cherry on the cake, we'll be able to visualize the results on a nice 2D plot in the end, thanks to these 2 code sections. All right, but right now we need to finish this, so there we go. We're going to extract only 2 features in the end, and to do this, we need now, of course, to connect our LDA object to our dataset, but once again, separately the training set and the test set. And to connect it, well, of course, we need to apply the fit transform method to the training set, and then only the transform method on the test set. That's for the exact same reason as before. It is to avoid information leakage from the test set. All right, so let's do this. That's our next step here. So we're going to take first xtrain, right, which we're going to update to become the new xtrain after we apply this LDA feature extraction technique. And to do this, well, we need to take, of course, our LDA object, from which we're going to call the fit transform method, which will take as input, well, here, be careful. It's not going to be exactly the same input as before, because, with PCA, the fit transform method took only xtrain as input because it only needs the features to apply this PCA dimensionality reduction technique. But LDA is actually different. In order to apply the technique, it needs not only the features, but also the dependent variable, right? The dependent variable is a required element inside the equation of LDA. And therefore here in the fit transform method, we need to input not only xtrain, the old version of xtrain before we apply LDA, and ytrain. All right, so be very careful with this, whether you choose to apply LDA or PCA. For PCA, you only have to input xtrain, and for LDA, you have to input both the features xtrain and the dependent variable ytrain. All right, final step. Well, now that we have an LDA feature extractor object fitted to the training set, well, we can apply it to the test set by only calling the transform method, right? It doesn't make sense to fit it again to the test set because the test set is supposed to be new data on which we deploy our model like in production. Therefore, we must only apply the transform method here, and therefore I'm updating our xtest variable the following way by first calling our LDA object from which we're only going to call the transform method. And now, according to you, does it need to take only xtest as input or xtest and ytest? Well, obviously, it only needs to take xtest because we're not supposed to have ytest, you know? Xtest is like new data on which we're going to deploy our model. Then we'll get our predictions in ypred, you know, and we'll compare ypred to ytest. But we're not supposed to have ytest because ytests are the real results that contain the hidden truth, you know, the ground truth. So, of course, here we only need to apply xtest, and the reason why we could enter ytrain here is because indeed we're supposed to get the ground truth of the training set. Otherwise, we wouldn't be able to train our machine learning model. All right, so xtest, and there we go. Not only the implementation of LDA is over, but also the whole implementation is over as well. So now we're going to do this run all now that we, uploaded the dataset into the notebook, so we're 100% ready. And let's just remind what we want to improve compared to previously. Well, in the principal component analysis implementation, we had, when obtaining the confusion matrix, only one incorrect prediction, resulting in having an accuracy of 97%. And in the test set results, which are the most interesting ones, well, we had indeed an almost perfect separation of the three classes. And now we're going to see if with our new feature extracted from LDA, well, we can get a perfect separation of the classes and therefore a 100% accuracy. Are you ready? Let's do this. 3, 2, 1, go. Run all. So now all the cells are running, and there we go. Oh, there we go. We just had a 100% accuracy. So in other words, our logistic regression model was totally able to classify perfectly our three classes by separating them separately. And that's exactly what we're going to see in, the test set results. Because indeed, well, we almost had an incorrect one here, but as we see, the real wines, which are all the points here, red, green, and blue, fall into the right prediction regions. That red prediction region, where our model predicts that the wine belongs to customer segment number 1. Then this one, where our model predicts that the wines belong to customer segment number 2. And finally, this prediction region, where our model predicts that the wines should be recommended to customer segment number 3. And thanks to these new extracted features, LD1 and LD2, well, this time we have a perfect class separator. In other words, we have a perfect classifier. And if you're wondering, how did LDA manage to separate perfectly the classes, whereas, in PCA, we could see that it was very difficult to separate, the wines of the test set, especially this one. This one falls in the middle of the red wines. Well, that's because the extracted features are different. They're not the same as PC1 and PC2. They are, in some other dimensions in which, well, this time it is possible to separate perfectly the classes. And that's why this time it works. We are, in other words, in another dimension. Okay, so I guess now we don't have much of a challenge because it's impossible to beat this. This is just perfect. I remind that I did not make this dataset. It's a dataset taken from the UCI ML repository. So it's very close to a real-world dataset. But there you go, that shows the power of this dimensionality reduction technique, linear discriminant analysis. So now we're going to move on to the next practical activity, the next section on this time kernel PCA, and we can just hope that we'll get, at least as good results as PCA or some as good results as LDA. In other words, let's hope that we get maximum one incorrect prediction. So I'll look forward to seeing you in this next section to implement kernel PCA, and until then, enjoy machine learning.